Okay, 4 o'clock. Welcome back to ME2002, also known as your favorite class. Yes. All right. Today we're going to start in on curvilinear motion. Notes are posted on Canvas if you want to follow along there. And that's what we're doing. Finally, some like real dynamics. Not that the 1D stuff wasn't real, but now full real 3D motion. Yes. All right. Homework number 5, which is on rectilinear and a little bit of curvilinear motion. It's going to be due next Tuesday, so make sure you take a look at that. You should be able to do all the rectilinear stuff at this point, which is questions 1 through 4. And after today, you should be able to do 5 and 6, which are the sort of preliminary curvilinear motion problems. All right, so let's get into it. By the way, I posted a new handout for the homework. It sounds like most of you saw my email, so there's a typo in the solution for the original handout, but I fixed it. Thank you to Mr. Warren Burton for that. Okay, we're not 2001, we're 2002. Okay, so where we left off, we were talking about rectilinear motion, which was motion of a particle in one dimension. And we explored not motion of just one particle, but motion of two particles relative to each other and that sort of general relationship. And that's a nice introductory stepping stone, a little baby step, into what is sort of like true curvilinear motion. And that's what we're going to start exploring today, is motion not just in one dimension, but in two dimensions. And generally we would call that 2 and higher dimensions. And generally we would call that curvilinear motion. So that's the topic that we're on today, and we'll get going on that. So here we go, curvilinear motion. We're gonna actually feel like we're doing some real dynamics today. Yeah, baby. All right. So curvilinear motion, let's define this. We'll first just talk about particles. So particles that move along a curve, so not a straight line, are said to be in curvilinear motion. Okay, so not straight. So not 1D, are in curvilinear motion. Here we're specifically just talking about particles. Okay, and just like we went through a derivation for relationships with position, velocity, acceleration, and time in 1D, we're going to expand that now to 2 and 3D. All right, so let's derive those equations. So consider a particle moving through space. On a curved path. My hand is like really jittery today. I feel like I had too much coffee. God. I don't know if it's better for me to like drink too much coffee and have like a little bit of a shaky hand, or fall asleep in the middle of lecture. I don't know which is better. So I'm going with, there's no such thing as too much coffee. Okay, have you ever seen the Futurama episode where Fry drinks 100 cups of coffee? It's an amazing episode. So if anybody likes Futurama out there, go watch the episode where Fry drinks 100 cups of coffee. It's awesome. Okay, so we'll consider a particle moving through space on a curved path, and let's just start with a traditional XYZ coordinate system, all right? So traditional XYZ coordinate system, all right? So the picture in your head that will soon be on paper, something like this. Your standard XYZ coordinate system. Right. And you've got a particle that exists out in space that's moving from one location to another along a curved path. So here, let's say that we've got some particle P. All right. and it's moving along some curved path. Let's make the curved path here in green. Okay, so here's my curved path this particle happens to be moving along. And let's say that it's moving from P to P prime in some time interval delta t. All right, so there we are at P. And sometime later, as it's moving along its path, it's going to be at a new position P prime. Sweetness. All right. Now I'm interested in sort of the kinematics of this, so relating position, velocity, acceleration, and time. And so we want to come up with some expression for velocity acceleration as a function of time, and this time interval over which that acts is going to help us do that. Okay, so we'll say it's originally at a position vector of r. Okay, so in this image, if we're thinking of a traditional position vector emanating from the origin, here's my position vector r that locates P. And it moves to, let's say, r prime. So moving here. All right, we know from previous discussions that the velocity of this particle after it moves from P to P prime is the change in that particle's position normalized by the amount of time that it took us to get there. All right, so in this situation, we can come up with a new vector that's the vector that points to P prime from P. Let's call that just delta r. All right, so this is our change in position, delta r. So change in position is this delta r. And the change in position over a certain time interval is the velocity. So over time interval, delta t is average velocity. So specifically, my average velocity, which is a vector, is this change in the position over the change in time. This particular definition of the velocity just has to do with some fixed amount of time. It could be a second, it could be a day, whatever. This is just your average velocity over that particular time interval. All right, so no specified instantaneous velocity here. This is just a very general definition of what your average velocity over some time interval might be. It's whatever your change in position is over that change of time. All right. Now, most of the time when we're talking about velocity, you're interested in your instantaneous velocity. So when you're driving in your car and you're looking at what's my miles per hour, that's an instantaneous velocity. That is, what is your velocity at that particular time? So if you're interested in what is an instantaneous velocity, basically you want to take the limit of this expression as time goes to 0. Okay? Instantaneous velocity as delta t goes to 0. So more or less, we're just going to employ calculus techniques and say that the instantaneous velocity, which will sort of drop the average here, is the limit as delta t goes to 0 of this delta r on delta t. If we know this concept in calculus, you can rewrite this in the differential, which is probably the more accepted way to see it, and say that the velocity here is the derivative of the position vector r as a function of time, differentiated over time. Okay. So that's your most general definition for velocity. We saw this in 1D, so this should not really be a surprise. But there's a little bit more complication that happens in 2D that we sort of want to talk about. All right, a couple notes here. Note number one is that the velocity is always tangent to the path. Okay. Why is that? Well, if we think about our original figure up there, and we think about shortening that time interval to a very, very small amount of time, the idea when we're taking our limit as delta t approaches 0 is the idea of, okay, our position vector is here, but it's sort of like as we are taking our delta t closer and closer to 0, this point P here is moving closer and closer to our original position. And if that's the case, this delta r is going to approach a position that's tangent to this path at point P. Okay? You can think of it that way physically if you'd like, or if you just understand from calculus that like the derivative of a line is the slope of the line that intersects or touches at that point, that's another way to sort of think about it, right? So think about like the derivative of this line at point P is going to be something like this guy here. Well, that's a spatial derivative, but the time derivative also has that same effect. Okay, so that's interesting to know. And another thing that we'll say is the magnitude of the velocity is the speed. And we talked about this in 1D, but I just want to hammer this home again. Usually given with the letter capital S, which is the magnitude of this velocity. We'll talk a little bit more about speed in the first example problem we do here. Okay. So that's your velocity. You can do a very similar thing for acceleration. All right. It's a very similar idea here, is that similar to velocity, the average acceleration over some time interval again is a vector. It's the change in the velocity over some time interval. Okay. If I'm back in my three-dimensional drawing here, again with the path of my particle, here's P, here's P prime. Well, the velocity is going to be tangent to the path, so the velocity at point P is sort of something that looks like this. So here's the velocity of P, and here we are tangent to the path. Here's like the velocity of P prime. So if I thought about taking those two vectors and both having them emanate with their tails at the same location, let me make that blue so it doesn't confuse you. here would be like the velocity of p. And if they're sort of tails are emanating from the same location, maybe here's the velocity of p prime. So that change in velocity would be here. This would be your delta v in this situation. Right. So this change in the velocity vector, normalized by the amount of time that it took to go from, let's say, p to p prime, would give you your average velocity or average acceleration. For instantaneous acceleration, again, taking the differential. I'll just cut to the chase here. It's just dv dt. That's your instantaneous acceleration. This is probably the most generic form of the acceleration equation. It's a function of the velocity and time. All right. Now, velocity was tangent to the path, but in general, acceleration will not be. All right. So there's no real relationship there, or kind of catch-all like the velocity is tangent to the path. So I'll just say here, in general, acceleration is not tangent to the path. Acceleration is really only tangent to the path if you're moving in the same direction for some short amount of time interval, right? So as I'm speeding up or slowing down on the highway, I'm accelerating and decelerating in the direction of the path. That's probably the only time that it really is tangent to the path, when you're actually moving, slowing down or speeding up in the direction of the path. So sort of a short-term one-dimensional motion. Okay. Now, we've talked about derivatives of vectors briefly before, and now it's time to like put our math pants on and really dive in on derivatives of a vector so that we're all crystal clear on this. And as we move forward with our curvilinear motion, we're going to talk about motion in frames that might be rotating and frames that might be translating. And so we have to be able to talk about derivatives of unit vectors that may be rotating, derivatives of unit vectors that may be translating, and everything associated. So we need to just really beat the math out of it right now for a slide or two, just like we did for double integrals and triple integrals. We need to have like a teaching moment for derivatives of vectors. I mean, I believe that you probably did vector derivatives in your math class, but I want to sort of talk about it in the dynamic sense anyways. So let's have a little aside here for derivatives of a vector and really dive in on it. Okay. So we'll just write it with some arbitrary vector for now, and we'll work in rectangular components for now. So let's say we have, or we'll consider a vector, let's call P, with rectangular components. Okay, so here is the vector P that's got Pxi hat plus Py j hat plus Pz k hat. This is your vector in typical rectangular components. You could think of a position vector if you'd like, as an x coordinate, y coordinate, z coordinate. You could think of components of velocity, x, y, and z components of velocity, so on and so forth. All right. Now, in general, what we're going to see in this class is that the individual components that make up the I direction, the j direction, and the k direction, these individual constants may vary as a function of some other parameter. We've seen let's say, the acceleration as a function of position, right? We've seen velocity as a function of time, etc. So let's say that each one of these individual constants that sort of dictate the rectangular components of this guy might be a function of some other variable, and we'll call it u here. So we'll say individual scalar components of P may be a function of some other scalar value. And let's say for now that that scalar value is u. That u might represent a position, that u might represent a time, that u might represent a velocity coordinate, something, all right? And so if we want to be very crystal about how we're representing some vector p, this vector p, which is a function of that scalar, I don't want to draw mu, I want to draw a u. Here is going to be something like you have an x component, which might be a function of u. Think of an x component as a function of time, for instance, plus your y component, plus a z component, which define sort of your vector. And they each might change independently. Px might change different as a function of u than py changes. All right, they could all have their own sort of functions. You know, an example, if you want to keep it sort of concrete, is a position vector as a function of time. Right, which might be like some x position as a function of time in I, plus some y position as a function of time, j, plus some z coordinate as a function of time, k. All right, and we'll get to something that looks like that shortly, right? But it doesn't have to be time that is your variable. It could be something else, position, whatever. Okay. Temperature, maybe, who knows, all right? So now when we're talking about the derivative of something that looks like this, the derivative of just this arbitrary vector p driven by another arbitrary scalar u, we've got to really be meticulous about this, okay? So in rectangular components, if we're considering like the derivative with respect to u, it's the following. It's the derivative of px, which might be a function of u. Actually, let's be a little more clear about that. Keep forgetting my k hats. Here. Okay. The individual derivatives of each one of the components. And by product rule, you can expand each one of these, right? So if you think of this as like, you remember your product rule, u, and think of this as v, and the product rule for each one of these would be like u dv plus v du, right? Okay, so you have to be very explicit about the derivatives here, all right? So this would become sort of this combination, which is the derivative of the first term multiplied by the second term plus the derivative of the first term multiplied by the second term. Right. This is just being very meticulous about, executing the product rule for this guy. And similar. Okay. So here. Plus similar, okay? Okay. Now we have to sort of understand what each of these terms really is. And I just want to talk about each one of these two just for a second. And then, this guy and this guy are going to be more or less the same. All right. This, I think, is sort of relatively easy to understand, right? The derivative of the scalar function with respect to u. This would be like the derivative of the x position as a function of time, if you're having your position analogy. All right. So I think this one's pretty sort of easy to understand, right? It's more this one that I want to talk about here. All right. Here's the derivative of the unit vector in the x direction with respect to a scalar multiplied by that function that defines the vector p in the x direction. All right. Generally, we're talking about fixed coordinates in this class. When we have a fixed coordinate system, an XYZ coordinate system that's just in space, let's say it's sitting on the desk here. Bam! Wake up. All right. That coordinate system isn't moving. So the derivative of, let's say, the x direction with respect to any scalar variable, time, temperature, position, that guy isn't moving anywhere. He's not changing. So generally, this will be zero. But we're going to talk about later incorporating translating frames or moving frames. And later in the course, this term will not be zero, okay? So it's very important that you sort of understand, at least for now, where this idea is at least coming from in part, okay? So I'll say this sort of in a note form, is that for fixed coordinates, this term here will generally be zero. However, later we will start talking about motion in rotating frames. Okay, and so when I start incorporating these terms, and you're like, well, where the hell did that come from? Okay, well, now you know. Right? So we'll just say, for this fixed XYZ frame, this is true. And continuing with this idea then, this derivative of this vector P is just going to be the derivatives of the individual components. Yes, you got that shaky hand. I can't even make an X. My hand is just like shaking like crazy. Okay. So we've just kind of mathematically shown that if you're in a fixed coordinate system, those derivatives of those unit vectors I, j, and k as a function of your variable u are zero. So what this means in English is that the derivative of a vector that's given in rectangular coordinates is the summation of the derivative of the individual scalar components as a function of u. Okay, so let's put that into words here. It's a little bit complicated, but the derivative of a vector in fixed rectangular components with respect to a scalar variable. Okay, so here that scalar variable is u. Could be temperature, could be time, could be something else. Is the combination of derivatives of the rectangular scalar components of that vector P. Okay, so that's basically written in English what we have up here. All right, so why is this powerful or potent? Well, now we can just take this general model and apply it straight to our velocity and acceleration relationships. All right. So we apply this now to velocity and acceleration in a fixed rectangular coordinate system. Okay. So given a position vector, which is a position vector r, which changes with time, which here is like some x coordinate as a function of time in I, plus some y coordinate as a function of time in j, plus some z coordinate in k. Then the derivative of that position vector is the derivative of each of the scalar components that make up x, y, and z with respect to that variable t. Okay. Okay. Some alternate forms that you might see. This is Vx as a function of time, I hat, plus Vy as a function of time, j hat, plus Vz as a function of time, k hat. We utilized this relationship a lot with our 1D, rectilinear motion, okay? I was kind of a little lazy with that relationship, that Vx is dx dt, when I was writing it with 1D, but now you see it here much more explicitly with, proper mathematics. Another way that this is sometimes represented, and I freaking hate this notation, but you see it a lot in your, let's say, dynamics of systems classes. Oh God, this grosses me out. X dot. Ugh. Makes me want to puke. Y dot t. Z dot. Where the dot is meant to represent a time derivative. Oh. It's just, so, So these are very common ways to see velocity depicted. Forgot my K hat here, sorry. This is going to be your bread and butter for the next 2 weeks, okay? Bread and or butter. All right, same with acceleration. Okay, so you will see this as dbx dt I hat plus. That's one form. You could make the I'm not going to write it, but you could make the substitution here that Vx is dx dt and make this like dx dt, so you'd have a second derivative. I'm not going to write that one. That's kind of beating it a little too much to death. And then throw up notation. X double dot. Ooh. It's indicating 2 time derivatives. So fancy. I will never use this notation, but you'll probably see it in your dynamics of systems classes. Anybody taken dynamic systems or have had it yet? I think you have to take this before you can take that, right? Yeah, okay. I don't have the ME track, I guess, fully committed to memory. Whoops. I should probably have that committed to memory, to be honest. Good thing I don't have any exams on it. Okay. Right. One last comment I want to make here is if you're considering something like in this situation, like I don't know, let's say V. Let me make last comment. An equation that looks like V equals dr dt. If you're in 3D rectangular coordinates, this is 3 equations, right? And I'll be very clear about this, independent equations. All right. This is assuming that you don't have coupling, meaning your y position is not necessarily dependent on your x position, which might happen if you're thinking about giving the location of object in y space given its location in x space. It's not too far out of craziness, but most of the time the individual scalar parameters of your position are parameterized by time. All right. So that's your last comment here. Okay, enough math nonsense. Let's do an example where we use this stuff. And the example will seem sort of trivial or basic after we just went through all that math, but I think it's good to just be very clear in particular about our math language. Because later when we do rotating coordinate frames, you'll be thankful that I sort of went through all this vector mechanics. All right. So let's look at motion of a particle in 2D. Got a position vector here given by this expression. I want to determine the magnitude of the smallest velocity and when it occurs, corresponding position, direction of velocity, acceleration vector at the time. Then we're going to sketch position, velocity, and acceleration. All right, so this is 2D motion. We're starting a little simplistic, mostly so that I can draw this a little easier. So I'll give you a second to copy down, and then we'll do it. So here you can see where each of the individual components are. Sorry, I should talk into the mic. Speaking to the microphone. You can see here that each one of the like x and y coordinates is parameterized by time, which is like your independent scalar variable here. So if you want to think of the analogy with what we did before, where p was a function of u, here r is a function of t, where t is driving your scalar component x and your scalar component y that make up this position vector r. Are you with me on that? I feel like SpongeBob. Are you ready, kids? Did you guys grow up with SpongeBob? Like, what was the cartoon for you guys when you were like little? SpongeBob? Yeah, okay. Man, I grew up with like Looney Tunes, man. I'm like that old. Where Looney Tunes was like the thing to look forward to. I also watched Cat Dog when I was little. I don't know if anyone watched that, but and Hey Arnold, man, those are classics. Rugrats, classics. What's that? Jackson, what? Hey Arnold or Rugrats? Rugrats, yeah. Phil and Lil, the twins.
I grew up with Pokemon. I don't know about.
Oh, Garame grew up with Pokemon. He says in my ear. Gotta catch 'em all. Did you catch 'em all, bud? What's that? In 3 different games. You guys ever watch like speed running of video games? I've like kind of caught it lately. It's like all over Twitch and stuff. Like if you watch people speed run like Pokemon and they finish it in like an hour and a half, you're like, dude, how the hell did you do that? It's like insane, their strategies and stuff. It's like Squirtle all the way. You know. All right. Let's get on with it. Sorry, distracted. What's that Squirtle was? Oh, I got. Okay. Michael has very strong opinions on the best Pokemon, so, you know. All right, so we got a position vector given by, bam, here. All right. We want to find a couple of things, and I'll just, I guess, copy paste this because it just makes life easy. It's going to fit. Wow. Let's tone it down there. Jeez. Oh, too small. How was it 11 before? What? Okay, I guess we're back to 11, but whatever. All right, so here we are. Determine the magnitude of the smallest velocity and where it occurs. All right, so if we have a sort of this position vector that we're given, and we're asking information about velocity, well, we better come up with an expression for the velocity. So that's going to be step number 1. So let's do that. All right. So we saw that velocity is the derivative of the position vector with respect to time. And we know from all that vector nonsense that we just did that this is just the derivative of each of the individual components with respect to time. So if we go back up here and we think about this portion being like the x position as a function of time, and think of this portion here as like the y coordinate as a function of time, that sort of makes things all sort of hunky-dory and lets us define really how I want to write this to reinforce what I just taught a little bit more clearly. This is dx t dt I hat plus dy t dt j hat. Since we're only in 2 dimensions, I'm only going to, utilize those 2 portions of the equation. All right, well, pretty easy then to sort of get your velocity as a function of time. Just basic derivatives of polynomial equations here. So the derivative of the x coordinate as a function of time is going to look something like 2t minus 8 in the I hat plus, what would be 1t plus 2. So I'll just write this as t plus 2 in the j hat. And why is this feet per second? What is this? This should be feet. Get out of here, seconds. Okay, this is feet. Sorry about that. This here now is feet per second, if we're assuming time is in seconds. So this is generally my expression of the velocity. But what I'm asked in the problem is the magnitude of the smallest velocity and where it occurs. Damn, it got complicated already. All right, so I'm interested in determining where the magnitude is the smallest. So if I have some expression here that tells me what the velocity is in the x and the y directions as a function of time, and I'm interested in the magnitude of the velocity, I probably need an expression as a function of time for the magnitude of the velocity. So how do we do that? How do you determine the magnitude of a vector if you have multiple components of that vector? Think back to your statics days. Yeah, Kenzie, do it. Yeah, Pythagorean Theorem. That's good. Yeah, right. That's the idea. Is you have some component in the I direction, some component in the J direction, and this is a function of time. This is a function of time. And so if you want the general magnitude, you're interested in what is the magnitude of like the hypotenuse there, right? That's generally the idea. And so in math language, how we would execute that is to say that the magnitude of the velocity, which we said before was the speed, I'll use capital S, is the square root of the sum of the squares of the components that make up that velocity. So the x component is 2t minus 8 squared, plus the y component is t plus 2 squared. That is my speed at any time t. Okay. Given that expression for the speed of the particle at any time, how do I figure out when the speed is minimized? Kenzie gonna have to save you boys again? Kenzie, do it. I think you're right. Keep going. How do you get the minimum of a function in calculus? Did you guys pass math? What? All right, minimum. I'm disappointed. Occurs when the derivative of this velocity is equal to 0, right? Max and a min occur. All right. So I need to take the derivative of this and set it equal to 0 and figure out what time makes that minimum or maximum. Yeah, that derivative looks disgusting, right? Yeah, okay. But if you're a little bit smart about it, you don't have to go through all the nonsense. What do I mean by that? Well, hopefully I can convince you that we don't have to deal with the 1/2, right? Because maybe I can convince you that the minimum of this velocity will also occur, I guess minimum or maximum, when generally just the inside of that square root is maximized, okay? Right? Sorry, I want the derivative of this. Okay, because if the speed is this expression, then the speed squared would be this expression to the 1. We all on board with that? Okay, so if I take the derivative of this, I'm still going to minimize the speed. We okay with that? All right. So then, the time derivative of all this stuff is going to look something like times the derivative of the inside plus derivative of the outside times derivative of the inside equals 0. Y'all okay with that? It's much better than taking that like square root derivative. That would be annoying. Caleb agrees. You can expand this. It'll be 10t minus 28 equals 0. Okay. Or t equals 2.8 seconds. Okay, so this is the time where we have either a local minimum or a local maximum of the speed. You could plug in times plus or minus this value to determine whether it's a maximum or a minimum. I'll save you the trouble. Okay, it's a minimum. Okay, so the minimum time or the minimum speed occurs at this time. Okay. And our speed, we know from our equation before, is, I'll just plug in the values here. So here we would have 2t minus 8 squared plus t plus 2 squared to the 1/2. So this here is something like 2 times 2.8 minus 8 squared plus 2.8 plus 2 squared to the 1/2. And so my minimum velocity here is 5.37 feet per second. Anyone checking my numbers? Jackson's checking me. Nice. Thank you, good sir. Sometimes I make boo-boos, so it's good to have someone check. Notice there's no directionality associated with this, because this is I guess that would be more appropriate. The minimum of the speed is that value. All right, a little bit complicated, but I think you have all the tools and the power in your tool bag to make this happen. All right, so that's part A. We're done with. Let's move on. Let's go to this next part, the corresponding position at that time. The rest of this is sort of easy. I need the position at t equals 2.8 seconds. Well, I'm just going to plug 2.8 in for my time variable at each one of those scalars that tell me the x and y position as a function of time. So here, the position at 2.8 seconds is I have to go all the way back up. I'll remind you that we have something like t squared minus 8t plus 7. So it's going to be 5. Why did I do that? Why did I write 5.37? All right, 2.8 squared. And I forgot my 0.5. God. Okay, t squared. Okay. Yikes. 2.8 seconds squared minus 8 times t, just 2.8 seconds, plus 7 in the I. And I'm going to add to that what's going on in the j. This is 0.5 times t squared. This is 2.8 squared plus 2t. That's 2 times 2.8 minus 4 j. So the position of the particle at the time when it has the lowest velocity or the least speed is the position at time is 2.8 seconds, which is negative 7.56 I plus 5.52 j. Feet. All right, maybe I think about starting to sketch this. It's kind of the last thing that this problem asks for me. So let's maybe think about making a sketch, and we'll add to the sketch as we go. All right. So my particle at this particular time, which is t equals 2.8 seconds, it's at location negative 7.56, positive 5.52. So let's just call that here, because that looks about right. So here I'll say that's where my particle is located in this two-dimensional space at 2.8 seconds on the clock. All right. Let's think about drawing in the velocity and acceleration vector of this guy at that time as well. And so we'll need to execute the next parts of the problem. That is calculating the velocity at this particular time. So you can go back to your velocity equation. Here we had something like 2t minus 8. So this is 2 times the time minus 8 I hat plus, what is the j component? It was t plus 2. This is 2.8 plus 2 j. Okay, so my velocity at this particular time here, negative 2.4 I plus 4.8 j. So slightly to the left and a good amount upwards. I want to think about what that might look like. Slightly to the left and maybe about twice that value upward. This would be a good velocity vector approximation. Okay. Lastly, d, acceleration. Well, I would need the derivative of the velocity to execute. My velocity in the x was something like 2t minus 8. So the acceleration here, pretty simple, 2 I hat. And my velocity in j was t plus 2. The derivative of that is just 1. So that's pretty simple. Feet per second squared. If I wanted to indicate this on my figure, maybe draw myself an acceleration vector. How is the velocity of this thing changing? 2i, 1j. 2i, half that amount in j. Maybe this would be a good approximation to the acceleration vector on that guy. All right. So there we are. Let's put our position vector in here for completeness. All right. So since the velocity is tangent to the path, maybe my path is something like this. That's a guess. Probably a good guess. And since my velocity is kind of changing to the right, the acceleration is going to sort of be moving this velocity vector to the right. That's why I made sort of the curvature in this general way. Right? Okay, so we'll take a break here. 5:04. Come back at, I don't know, 5:12, 8 minutes. Making it pretty. Bring like the colored pencils. I kind of like writing on this writing bag because I can just like quickly change the colors. It's kind of nice. If I have to do that on the board, I have to like, I have to like invent like a utility belt like that, or like get the markers out and like fast enough to make it useful. What other classes are like typical right now in the sophomore? Yeah. Are you you like on the standard path? What else do you have? Organizational psychology. Learn in that class. They teach you. Are you in that too? Yeah. Yeah, that's what he was. So what are like the questions? What are the prompts? Are they using any prompt essays? Oh, right. Wow. Writing your own question? You have to answer your own question too? Wow. Interesting. A lot of current events talking about organization. Oh my goodness. I bet there's going to be so many people that are talking about January 6th and psychology behind that sort of really interesting. Come at it from a different. Okay. You lost a couple members, got a couple. Your response. I should at least start. Buying the hog. Yeah, every single quarter. That's a new. It's what I go through. Team of people. Yeah, the longer this like COVID thing goes on, the more it's like disheartening for me. I like to chat with the students in like the downtime. It's kind of like right now. Jackson knows from. No. Yeah. I just feel like it helps my teaching to understand students a little better. Talk to me if we have 4 hours. Yeah. I really want that. You get everything done in like 2. Yeah, right, of course. It's such a bad model. There's so many reasons why that's just a terrible teaching model. It's kind of nice though, like if it's busy in one area, you can put it up. Yeah, that's yeah. The biggest problem is just like the discipline aspect of it, right? Most people just don't have the discipline to sit down and start a business for 3 hours on something that's not due for 2 months, right? It's hard to get people to do homework problems the day before it's due or whatever. Yeah. I'll just sit down and do it. Right. Most people don't have that mentality or that mindset, I would say generally. I've run classes before where homework has been optional, and I haven't had it as part of the grade, and the grades in those classes are significantly lower. That's because people, I still give out the homework and I still make it available, all the solutions and everything, but people, they don't have the discipline to sit down and do it if it's not, part of their grade. In general, I'm not saying that that's true for everybody, but I've tracked the numbers. It's easy to see, right? That's why I'd make like homework a requirement in my class and sort of spend a lot of time formulating them. I think people just don't have as much the discipline to just sit down and do it. So, yeah. Anyway, teaching philosophy. Oh. Some of my colleagues disagree, and we chat about it. It's interesting discussion. Their mentality is if they don't have the self-motivation, then they're not going to, they should have their own intrinsic motivation. Some of my other colleagues argue, and well, there are many. No, there are many that have that mentality, and I understand where they're coming from, but they criticize me and say that I'm holding your hand by force feeding you homework and all this sort of stuff, and I understand their criticism, but I think generally the learning experience is better if you sort of force the homework. What's that? Yeah, they don't have to grade it either, right? Well, yeah, I understand that, but yeah, it's an interesting conversation to be had. But there you go, your organizational psychology. You got more than you bargained for there, Jackson. All right. Okay, baby. Let's keep it moving. Now, that's a nice example that we started with. You're seeing position, velocity, and acceleration, where each one of the individual components is a function of time, and you're looking at the derivatives of each one of the individual components and all that sort of stuff. And cool, interesting. We need to start getting to a situation, though, where we're using not just your standard rectangular coordinates, but we're using some other coordinate system that might be useful for, let's say, circular rotation, a cylindrical, rotation in a cylinder, like moons around a planet or satellites around the Earth or whatever, rotating coordinate frame, a moving coordinate frame. And sort of the first step towards getting there is talking about relative positions of particles, which will translate or sometime later turn into positions of two coordinate systems relative to each other. So step number one is talking about relative positions of two particles in space. And then we're going to eventually go to positions of two coordinate systems relative to each other in space. All right, so the next step on our journey is relative position with a translating frame. Okay. We've sort of talked about relative position with one dimension, but that's all the stuff we did in one dimension is relatively straightforward. When we go to 2 and 3 dimensions, things get a little bit more complicated. So let's just start off with some motivation of two particles in space. All right, so let's consider two particles in space. And at points A and B. So in your head, here's your origin. Oh, your typical XYZ coordinate system, X, Y, Z. And you've got two particles in space. One that's point A, here's A, and another up here is at point B. All right. We can define each of the positions of these guys using our typical position vectors. position vector which locates A, and position vector which locates B. No problem. Now we're going to get a little spicy. All right. Now what we're going to do is we're going to slap another coordinate system onto point A. And the reason that we're going to do that is because now we want to make a position vector that talks about where point B is in space relative to point A. So to do that, we're going to slap a coordinate system on A and talk about the position of B relative to A. So let's now consider a new coordinate system at point A. Right. And that coordinate system will be A, X prime, Y prime, Z prime. That's how you would denote it. The point at the center is point A, and the axes are X prime, Y prime, Z prime. And we're going to say that this coordinate system translates in space with point A. I forgot to bring my my connects for this lecture. Usually I like to bring my connects. You guys ever use connects when you were little, like the plastic toys or whatever? It's like the building block toys. Yeah, most engineers have. Okay, I like to bring those in because I like to have like coordinate system number 1 and then coordinate system number 2, which is point A, sort of translating in space. So hopefully you can sort of think about this. But the idea here is that if X, Y, and Z, and this should be like perpendicular. This is terrible. Sorry, RA, you got slashed. All right. The idea here is as A moves around, Y prime remains parallel to Y, X prime remains parallel to X, Z prime remains parallel to Z. That's what it means to translate in the frame. Okay, so X prime always parallel to X, Y prime remains parallel to Y, and Z prime remains parallel to Z. No rotation. Very important. No rotation yet. Okay, let's wait though. Okay. If this is the situation, then we can pretty easily define the position of B relative to A in the X prime, Y prime, Z coordinate system. The position of B relative to A is the position of A sorry, let's write this a different way. We want to end up with the final position of B, which is the position of A, so whatever it takes to get to point A, plus the position vector of B relative to A in this X prime, Y prime, Z prime coordinate system. Where the position vector of B relative to A is here. Okay, so it's pretty easy to see with vector math then that RA plus RBA is going to give you the position vector of B. Or you might want to rearrange to say that the position vector of B relative to A is going to be the position vector of B minus the position vector of A. Okay, this is specific for translating frame only. Here at O, the origin. If your coordinate system rotates, then things get messy, and we'll see that in short order here. All right. So with this general idea, and knowing what we know about derivatives now, since we've sort of talked about this, this here is your relative position in sort of 3D space. All right. You also may be interested in relative velocity equations. The derivative of your position vector of B with respect to A as a function of time. I'm not indicating here that this position vector is a function of time, but you can just assume that to be true. All right, I'm not writing it here, but you could assume that it is true. This would be the derivative of position vector B with respect to time minus the derivative of position A with respect to time. And this is why we see that it's so important that we have a translating frame at A, all right? Because this guy here is given in the A coordinate system, all right? So this is written in like your X prime, Y prime, Z prime coordinate system, okay? And if your coordinate system was rotating and not translating, remember what your derivative looks like, okay? Your derivative looks something like dr BA T dt is the components of the individual guys. So that's like dx t dt I hat plus d I hat dt xt, where this should actually be like a x prime because we're in that a x prime, y prime, z prime coordinate system. This would be like the first component of that derivative, and you would have additional bits, okay, for x, y prime, and z prime, okay? Hopefully we're with that. We require a translating coordinate system at A because if it was not translating, this would not be 0, okay? Hopefully we gather that and understand that. If your unit vector in the what would be the I hat direction is not staying in the I hat direction as you move through space, then that direction, that unit vector, is not consistently pointing in one direction. If you're rotating around, you got some issues to deal with in this term. All right, that's why it's sort of important at this point that we stick to translating frames. More to come on that a little later, so don't fret too much. But trying to give you a little motivation on why we require the translational frame here. So we'll say since d I hat dt equals 0 for a translating frame, we can proceed with the traditional description of the velocity, which is that the velocity of B relative to A is the velocity of B minus the velocity of A. Similar for acceleration. The acceleration of B relative to A is the acceleration of B minus the acceleration of A. We're like tiptoeing up to the precipice of rotating coordinate systems, so we're just not quite getting there. Okay. So let's make some notes here. VA and AA and VB and AB are velocities and accelerations of particles A and B in the O, X, Y, Z frame. That is your fixed coordinate frame, all right? It's fixed in space. It's not moving around. The other guys, VBA and ABA, this is the velocity and acceleration of particle B with respect to A in the A, X prime, Y prime, Z prime frame. All right. How are we doing? We ready to cry yet? I'm about ready to cry. It's confusing a little bit, talking about all this stuff. All right. I'm debating whether or not I have time for this example. Yeah, we're doing it. Okay. Example problem. Usually I let you out early, but I think we might go to 5:50 today. Sorry, guys. Mixed units, my favorite. Auto A, traveling east, 36 kilometers an hour, crosses the intersection at that particular time shown. Auto B starts from rest 35 meters north of the intersection and moves south with constant acceleration. Determine position, velocity, and acceleration of B relative to A 5 seconds after A crossed the intersection. So what position, velocity, and acceleration does B have in the translating A frame is what we're asking. Complicated. Can we read that okay? You want me to blow it up a little? Bam. That's sort of what we're asking in this problem in sort of math language. Okay, so we'll get moving on this. The sooner we start, the sooner you get to go home. Okay. So this is what we want. We want this position of B relative to A, velocity of B relative to A, and acceleration of B relative to A at 5 seconds. Sure, sometime. All right. Gonna be easiest for us to just come up with a general expression for RBA, VBA, and ABA as a function of time, and then plug in our 5 seconds after all is said and done. All right, it's just usually how we attack these problems, get it in the general form as a function of time, and then move forward. So we need this RBA, which is something like the position of B minus the position of A. We also need VBA, which is the velocity of B minus the velocity of A. So most of my work in this problem is generally going to be defining what are those values on the right-hand side. Once I get those values as a function of time on the right-hand side, my problem becomes pretty easy. So we're going to define all these guys here as a function of time. All right, let's start with car A. All right, what am I told about car A? It's moving east at a constant speed of 36 kilometers an hour. Okay. So I know in my fixed frame that I'm looking at from above, the velocity of A is 36 kilometers an hour, and it's moving east. Velocity needs a direction. I will convert to meters per second so that we can sort of have similar units to work with in this problem. And here, if we do that, this will be 10 meters per second I had. Okay. So bit number 1's kind of out of the way. That's nice. I'm told that it's moving at a constant velocity of 10 meters per second. That means my acceleration of this guy is 0. All right, making my way. Zero vector, if you like. All right. Now, I also need my position of object A. For that, I lean on this. So we would have something like the position differential of object A is the velocity of A dt, our general form here. Okay, I can integrate. From initial position to final position of this particular guy. And here from initial velocity to some velocity v. Sorry, not velocity, this is integrated over time. All right. So this would be minus your initial position equal to the integral of the velocity of A in vector form. Okay, so here we are. Here's my velocity of A in vector form. Integrating this with respect to t. Assuming that time 0 is equal to 0, I guess that's probably a safe assumption. Then we're just going to have 10 t I hat meters, where t is in seconds. I would need to define some initial position of car A at this point. And we're working at this point in the sort of global fixed coordinate system. All right. We're talking about the position of A in the global coordinate system, or the fixed coordinate system. So we want some initial position of A in the fixed coordinate system. So we need to define this guy. And let's look back up at our problem, see if we can define an initial position. So it says here, it's traveling east, automobile A crosses the intersection shown. Okay. All right, so as it's crossing the intersection shown, we have this constant speed. So we're free to sort of choose where our fixed coordinate system is located. Let's locate that coordinate system right at sort of vehicle A, or right at the middle of that intersection, maybe is more appropriate. So with that idea in mind, our origin at this particular point happens to be right where A is. And so this initial position here is just 0. I'm assuming that I'm just like starting right at the location of the fixed coordinate system right when A passes that intersection. So we can basically take like the center of the intersection as like the fixed coordinate system in this situation. All right. So that means here that my position vector of car A at any particular time is just 10 t I hat meters. Okay, and here will be specific t in seconds. We need some unit for time to know. This sort of makes sense. You know, if we're thinking about a global coordinate system and this guy is sort of moving to the right at a constant, you know, this is 10 meters per second. If the guy's just moving to the right at a constant 10 meters per second, well, the position at any time t is just going to be the time times 10, right? In the I hat, right? So 10 seconds later, I'm over here at 100, if our velocity is constant, all right? Makes sense. All right, moving on. Car B, similar idea. We're told some information about car number B, geez. About car B. Specifically now we're told about its acceleration though. 1.2 meters per second squared downwards. All right. We have here now constant acceleration, 1.2 meters per second squared. All right, so here for car B, I know something about its acceleration. And I know it's negative 1.2 meters per second squared downward, j hat. I will go through the sort of the same rigmarole to get velocity by integrating. So my integral here of from the initial velocity of B to some velocity of B, I'm integrating over the velocity, is here this integral of AB dt. All right, so here we have velocity of B minus the initial velocity of B equal to the integral of our acceleration of B integrated over time. So here this will just be negative 1.2 t meters per second in j hat, where t is in seconds. So if I'm interested in the velocity as a function of time here of car B, I need the initial position or the initial velocity of car B. Fortunately, in the problem, I'm told automobile starts from rest. All right. Okay. So that helps me settle my integration constant here to 0. So finally, I can write that the velocity of car B as a function of time is negative 1.2 t meters per second j hat, where again, t is in seconds. One more integration. I'll cut to the chase. Hopefully we're all kind of comfortable with the integration at this point. From 0 to t. From initial position of B to random arbitrary position of B. This gets us position of B minus initial position of B equal to the integral of this velocity. It's going to be negative 0.6 t squared. J hat, here's meters. I need to reconcile my integration constant of the initial position of car B. And remember, we're talking about the fixed coordinate system. Going back up to my problem, I have my fixed coordinate system here. So we see in the problem, car B originates at a location of 35 meters away from that fixed coordinate system. So my initial position of car B is just 35 meters in j hat. That means my position vector of B as a function of time is negative 0.6 t squared minus 35 j hat meters. Okay. The rest is just, yes, thank you. The rest is just taking what we know in our fixed coordinate system and applying it to our relative equations for the coordinate system at A that's translating. So then, if we're interested in the acceleration of B relative to A, now as a general function of time, we know that that is going to be the acceleration of B as a function of time minus the acceleration of A as a function of time. I can just bang right through this. Acceleration of B here, negative 1.2 meters per second squared in j hat. And I'm going to subtract from that my acceleration of A, but acceleration of A is 0 because we're moving at a constant velocity. So the acceleration of B relative to A here, negative 1.2 meters per second squared J. And so if we're sort of trying to solve the problem and discuss what is the acceleration of B relative to A at time t equals 5 seconds, which is what we're after in this problem, well, t does not appear in this equation. So for all time, we are valid. If you want to be very specific about answering the question, you can say the acceleration of B relative to A at time t equals 5 seconds. Just to be clear to the reader, you can write directly. That is your acceleration at t equals 5 seconds. Same ideas for velocity and position. I won't beat it to death. You get the idea. It's the velocity of B as a function of time minus the velocity of A as a function of time. We've already got these things. The velocity of B is negative 1.2 times time. J hat minus velocity of A is 10 meters per second constant in I hat. Okay. So the velocity of B relative to A at time t equals 5 seconds is going to be negative 6 j hat minus 10 I hat meters per second. So that's sort of the second answer to this problem. And lastly, the position of B relative to A is the position of B as a function of time minus the position of A as a function of time. In general, as a function of time, this is going to be something like the position of B, which is negative 0.6 t squared plus 35. Remember, we started 35 meters above that coordinate system. J hat minus the position of A at any function of time, which is 10 t I hat, where t is in seconds, and the units here are meters. Can plug in here and get the position of car B relative to A at time t equals 5 seconds. Negative 50I plus 20J. Meters. Okay, so car B is 50 meters left of A and 20 meters down from A at 5 seconds. So this is how B appears in the coordinate system that's right on top of car A, moving with car A. All right, I know it was a long day today. Thanks for sticking with. We'll talk about rotating coordinate systems on Tuesday. So long.